This is the beginning of Unit 7, and we'll be looking here at the textbook sections 10.1 through 10.4. We'll be talking primarily in this unit about other types of systems for writing equations. First, the parametric system, and then the polar system. So 10.1 is all about parametric equations. Up to this point, we've always represented a graph just by a single equation involving two variables, right? Y was a function of x. So you had an input variable x, an output y, and you could plot the points on a graph. In this section, we're going to study situations in which three variables are used to represent a graph in a plane. We'll consider that x is itself some function of a third variable, t, and y is also a function of a third variable, t. When we write equations in this form, they're called parametric equations, and our new variable t we call the parameter. Now, we don't have to use t. We could really use any letter for this third variable. But in application problems, we usually think of that third variable t as representing the time, which is why t is often the default variable that we choose to use. All right, what we have here is just a quick little mathy definition of a plane curve, but essentially, again, it's just saying that if x and y are functions of t, together they form parametric equations, with t again being called the parameter. And we can graph these as some type of curve in the xy plane, denoted by c. Just a very mathematical definition of what we already said. So let's give this a try. Here's a set of parametric equations for us to work with. X is equal to 2t plus 2, and y is equal to 3t plus 4. We're going to try to fill in a table of values and then graph whatever this looks like in the xy plane. Okay? Notice this is the xy plane. The values of t themselves never appear on the graph. T is just used to get to the x and the y. So we're just going to plug in. If t is 0, for x we plug into 2t plus 2. For y we plug into 3t plus 4. And when t is 0, I'll get 2, 4. We'll keep going. If t is 1, 2 plus 2 would give me 4 here, and 3 plus 4 would give me 7, and so on. If t is 2, 4 plus 2 is 6, 6 plus 4 is 10. Plugging in 3 gives me 8, 13. Plugging in 4, 8 plus 2, 10, and 12 plus 4, 16. And let's see, I'm actually going to do 2 more here. 5 would give me a 12 and a 19. And I'm going to add 1 more. 6, 14, and 22. Okay. All right, let's go ahead and plot the points, x comma y. Again, the t's do not appear on the graph. Just the x's and the y's. So my first point is 2, 4. I think these are labeled by 2's. Yeah, so 2, 4 would be right there. And the next point is 4, 7. And then 6, 10. 8, 13. 10, 16. 12, 19. And then 14, 22. So it's pretty clear that these points form a straight line. And I'm just going to go ahead and draw that line. did not mean to put that as habit, but I'm not going to put any arrows on this yet. I want to talk about that later. All right, so there's the line that is formed by these two parametric equations. Because of all the math we know, it would not be hard to figure out the actual equation of that line in standard slope-intercept form. We could do that really quickly. Notice the slope. I could just do rise over run, right? It goes up 1, 2, 3, and over 2. Or you can see it here as well, right? Change in y is 3, change in x is 2. I can pick any point. I'm just going to use 2, 4 for my x and y. Sorry, move that so you can actually see what I'm doing. So I've got my slope 3/2 and my point 2, 4. And then if I just do y equals mx plus b, I have 4 equals 3/2 times 2 plus b. So b is 1. And this line is actually y equals 3/2 x plus 1. What I'd like you to notice about this equation compared to the original parametric equations is that the slope of my equation, 3/2, is actually the coefficients of t that have now been divided. Slope is always rise over run, or change in y over change in x. So unsurprisingly, it's the y coefficient that ends up at the top, and it's the x coefficient that ends up on the bottom. So I'm just going to say, if the slope can be written as b over a, then it must be true that in the original parametric equations, x was at plus something, and y was bt plus something. Okay? What is that something? Well, again, take a look back at the original parametric equations and notice that the 2 and the 4 that were added here were actually the x and the y value when t is 0. So I'm going to call those x sub 0 or x naught and y sub 0 or y naught. And that's just the point when t equals 0. So there's kind of a little recipe, if you will, for coming up with parametric equations for a line. If we know the slope of the line, b over a, that really tells us the coefficients, b and a, in the parametric equations for x and y. And then if we know sort of our starting point, where are we when time t equals 0, we're at some point x naught, y naught, those become the add-ins in our parametric equation. So formally, the parametric equations of the line with slope b over a that passes through the point x naught, y naught can be written as what I just wrote, x equals at plus x naught, and y equals bt plus y naught. All right, we're going to do some examples of getting this parametric equation, using it, comparing it to what graphs look like, so we can get a little bit used to parametric equations for a straight line. All right, the next question I'd like to investigate is the parametric form of the equation of a line unique? Let's try to write several more sets of parametric equations for the line in the example that we just did. And we're going to assume that t goes all the way from negative infinity to infinity to get the full line. We'll then address the question, in what ways does the interpretation of your equations differ from that of the original line? Okay. So, what I've got here is just a little homemade graph because I didn't happen to have any graph paper handy. And make this bigger so you can see it. I'm going to go ahead and I'm just going to plot my original parametric equations on here. That was x equals, what was it? Sorry, I can't even remember what the original ones were. Here they are. X equals 2t plus 2 and y equals 3t plus 4. And we already had the points over here, so all I'm going to do is recreate this on this larger graph. And then as we get some more examples, we're going to plot on the same graph so we can notice the similarities and differences. So I'm going to take these same exact points and I'm just going to put them on this bigger graph. So 2, 4, 4, 7, 6, 10, 8, 13, 10, 16, 12, 19, and 14, 22. All right. The first thing I'd like to mention is something that I kind of ducked before, but I want to be very specific right now about labeling some of these points. This point 2, 4, remember, was specifically the point when t equals 0. So this point corresponds to t equals 0. This next point I missed just a little bit, we'll pretend, corresponded to t equals 1. Right? When t was 1, we were at the point 4, 7. And then the next point, 6, 10, corresponded to t equals 2. So, because of the fact that we think of time as only running in one direction, right? Time only gets bigger. What this does is it gives my line a direction. As a generic line, y equals 3/2 x plus 1, we could be traveling this way or we could be traveling that way. But with parametric equations, we consider the direction of the line to be the direction of increasing t values. So that means the t values increase this way, I'd be traveling along the line in this direction. And we'll usually put little arrows on there to indicate that. All right, let's think about a couple of variations. I'm going to set this graph aside and we'll come back and add some to it in just a couple of minutes. My first variation is going to be to say, what if we keep the same slope, which was 3/2, but this time, what if I want to say, instead of having the starting point be here at 2, 4, what if I want my starting point to be, let's say, at 8, 13 instead? Well, what I've done is I've kept the b and the a the same, but I've changed the x naught and the y naught. So when I go to write my parametric equations, it's going to look like x equals a, so still 2t, plus x naught, which is 8. And y would be b, so 3t, plus y naught, which is 13. Notice what this does to our table of values. When t is 0, right, we're now just going to have an x of 8 and a y of 13. So we really did accomplish the fact that we're starting at the point 8, 13. When t is 1, 2 plus 8 is 10, 3 plus 13 is 16. When t is 2, 6 plus 8 would be 14. T is 2, right? Whoops, what did I do? Try that one more time. When t is 2, that would be 4 plus 8 is 12. And when t is 2, that would be 6 plus 13 is 19. And I'll just do one more. If t is 3, now I've got 6 plus 8 is 14. And 9 plus 13 is 22. So notice the points on the line haven't really changed, right? Those are the same points for x and y as I had here. 8, 13, 10, 16, 12, 19, 14, 22. They're all the same. The only difference is what's considered the starting point, t equals 0. So what I end up getting is exactly the same line, but this time the point 8, 13 is my t equals 0. And the point 10, 16 is my t equal 1. And there's t equal 2. And t equal 3, and so on. Okay. Now, depending on whether or not we want to allow for negative values of the parameter, sometimes we might just graph the line starting from the point where t equals 0 and going on. Or starting here, in this case, from the point where t equals 0 and going on. So parametric equations offer us a really convenient way to kind of restrict the portion of the line that we really want to look at. Okay. So the second one was our second version of parametric equations, which was x equals 2t plus 8 and y equals 3t plus 13. Okay. Notice, by the way, that the direction of increasing t stays the same. We're still going in this direction. All right, let's make another change. This time, I'm going to say my slope was 3/2, and I'd like to keep the same basic slope. The meaning is still 3/2, but there are other fractions that mean the same thing as 3/2, right? For example, 6/4 is still the same slope, just not lowest terms. What if I use that 6/4 as my slope to define b and a? And I think I'm going to go back to the original starting point. Let's let x naught, y naught go back to that 2, 4. Well, using our parametric equation forms, x is 4t plus 2, and y would be 6t plus 4. Let's make a little table of values for that one. Oops, t first. So if t is 0, I'd get 2 for x and 4 for y. If t is 1, 4 plus 2 gives me 6, and 6 plus 4 gives me 10. If t is 2, 8 plus 2 is 10. 12 plus 4 is 16. And if t is 3, 12 plus 2 would be 14. 18 plus 4 would be 22. Let's go ahead and see what happens to our graph using these values. Okay. So this third one is my equation. X equals 4t plus 2, and y equals 6t plus 4. So we still started here at 2, 4. That was our t equals 0. But then t equals 1 was 6, 10. And t equals 2 was 10, 16. And t equals 3 was 14, 22. So notice what's happened. We've actually gone up along this line twice as fast, right? I didn't finish labeling these first ones, but I probably should have. That would be t equal 3, originally t equal 4, 5, and 6. So notice, what used to take me 2 seconds now takes 1. What used to take 4 seconds now takes 2. What used to take 6 seconds now takes 3. Right? So by actually using a different form of the slope, not a different value, right? 6/4 is the same value as 3/2. We've kept the same line, but we've traveled along it faster. So parameterization is a way of controlling the speed at which you're traveling along your graph. So I'm going to say the graph is traversed, just a way of saying traveled along twice as fast. And I'm going to notice, because this is going to help me out later, that essentially what I did to go from the t terms here to the t terms here is I literally doubled to go twice as fast. So if I replace t with 2t, I literally double it, I'm going to go twice as fast. And we'll use that idea moving forward. All right, I'd like to look at one more variation here. For this third variation, I'm going to go back to the idea that when the slope was 3/2, right from the start, and this time I'm going to say, well, another way to write 3/2 would be -3 over -2, right? Same fraction, just a different form. And so I'm going to use this as my b and my a. I'm going to go ahead and keep the same starting point, 2, 4. So what is our equation going to look like this time? Well, let's see, or equations, I guess I should say. We would have x equals a, so -2t plus 2, and y would be b, so -3t plus 4. I'm going to make myself a little table of values this time. All right, starting out at t equals 0 again. Certainly if we plug in zeros, we're going to get 2, 4. Not surprising, that's our starting point. Plugging in t equals 1. -2 plus 2 is 0. -3 plus 4 is 1. Let's do t equals 2. Negative 4 plus 2 is negative 2. Negative 6 plus 4 is also negative 2. And how about t equal 3? Negative 6 plus 2 would be negative 4. And negative 9 plus 4 would be negative 5. Those are points that have not appeared on my graph up to this point. So let's add those in there. Here's the graph that we've been working on. And let's see, I started at 2, 4. So we start right there again. My next point was 0, 1. Here. My next point was negative 2, negative 2. There. And then the last one I have here is negative 4, negative 5. And my line is just slightly off. I missed by a little bit, but it should have gone through there. Sorry about that. So what's happening here is that, again, I started at the same point at t equals 0, but I'm traveling backwards along the line for t equal 1, t equal 2, t equal 3. So this time, the direction along my line would go this way. So what we're seeing here is parameterization can really control two different things beyond just the shape of the graph. It can control the speed that we're traveling along the graph, right? Like here where we doubled our speed. And it can also control the direction we travel on the graph. For the first three examples, we were going up to the right. For this last example, we were going down to the left. So both speed and direction of travel can be controlled by parameterization. Keeping that in mind, we're going to go ahead and experiment a little bit and see if we can creatively come up with some parameterized equations that do exactly that, adjust for speed and direction. So in example 2, we want to consider the line that goes through the points A, which is 3, 1, and B, which is 6, 2. And we're going to do a whole bunch of stuff with that, so I'm just going to kind of squeeze in this upper corner a quick graph of that line. It's from 3, 1 to 6, 2. And I won't prejudice it by putting any specific direction in at this point. We'll just leave it like that. All right, part A says to find parametric equations for the full line running in the direction from A to B. So for letter A, I want to go this way, right? From A to B. So what I'm going to do, going from A to B, I would consider my rise to be a positive 1 and my run to be a positive 3. So the slope, rise over run, would be 1 over 3. That defines the B and the A. The starting point, if I'm going to go from A to B, the starting point A is 3, 1. So that defines the x naught and the y naught. So putting the pieces together, I could say that my parametric equations would be x equals 3t plus 3 and y equals 1t plus 1. Let's try part B. This time I want parametric equations for, again, the full line, running in the direction from B to A. So this time I want to go in the other direction. Starting from B, going to A, I would consider my rise to be -1, and my run goes to the left, -3. So my slope, I would think of as -1 over -3. And once again, this defines my B and my A. My starting point this time would be B, 6,2. So there's my x naught and my y naught. And putting the pieces together then, x would be -3t plus 6, and y would be -1t plus 2. All right, part C. Find parametric equations for the line segment AB, for which travel from A to B takes 1 second. I think we actually already have this mostly done. We are going from A to B. So we'd be looking here, right? This is when was going from A to B. So we'd be looking at this equation, or this pair of equations rather. And we'll just double check that going from A to B really does take 1 second. Notice that if I go back to these parametric equations, starting out at t equals 0 is just going to start me out at the 3, 1. And if I plug in 1 second, 3 plus 3 is 6, and 1 plus 1 is 2. So I do start at A at time 0, and I end up at B at time 1. It took 1 second to get between them. So I actually already have the parametric equations that I need. The only thing is, notice this time I specifically wanted not the full line, but just the line segment. So the way we deal with that is just by restricting our t values. In these first two, we were essentially letting the t values be anything. Although we didn't explicitly state it, we were kind of under the assumption that t could be anything from -infinity to infinity. In this one, we're going to explicitly state, to get just that one little piece between A and B, we want to limit our t values to just the values from 0 to 1. So parametric equations that I already had, but adding on that restriction will keep me at just the line segment. All right, let's go ahead and take a look at part D. I want parametric equations, again for the line segment AB. Again, I'm going from A to B, so I'm going to start here again. But this time, I want it to take 3 seconds to go from A to B. So I only want to go 1/3 as fast. It's going to take 3 times as long, right? So I'm traveling at 1/3 the speed. So I'm going to use the same equations, but it takes 3 times as long. So 1/3 the speed. Well, you saw what happened in the previous example, right? When I basically replaced the t with 2t, it doubled the speed. So if I want to only go 1/3 as fast, I'm going to take my t's and replace them with 1/3 t. So I'm going to go back up to the equation I already knew, and I'm going to literally replace the t with 1/3 t. And so my equations just become x equals t plus 3, and y equals 1/3 t plus 1. left myself a little space because I'm going to add a restriction for t there. But let's just check and make sure this does what we expected it to do. I'll make our table of values here. When t is 0, we would get 3, 1. And then we wanted it to take 3 seconds to get to 6, 2, the value of b. So let's see what happens after 3 seconds. If I plug in 3, 3 plus 3 is 6. That's exactly what I wanted. And 1/3 times 3 is 1. 1 plus 1 is 2. So I have indeed gone from A to B in a total of 3 seconds. Now, if I want to restrict myself to just that portion of the line, I will have to say the t values are limited to just 0 to 3. All right, we have one more. In E, we wanted to find the parametric equations for the line segment AB. And this time we're traveling from B to A. Remember, this was the one here where we went from B to A. So I'm going to use this one as my starting point to do E. This time, though, instead of taking 1 second like it did originally, from B to A, I only want it to take half a second. So it takes half as long, therefore I'm going twice as fast. That means I'm going to replace my t's with 2 t's. So we had x equals, and let's see, I have a -3, and then I'm replacing the t with 2t, plus 6. And y was -1, and again I'm replacing the t with 2t, plus 2. So x is -6t plus 6, and y is -2t plus 2. To get just the line segment, we'll again have to restrict. This was the table for this one. I'm going to put the table for this one down here. At time 0 would be at the point 6, 2. And we wanted to be able to travel from B to A in half a second. So let's put 0.5 in for t. That would be -3 plus 6 is 3. And when t is a half, that'd be -1 plus 2 is 1. So notice we've done what we said we were going to do. That's B. We've gone to A, and we've done it in half a second. So I will restrict my t values to 0 to 0.5. So I only get the line segment, not the entire line. All right, hopefully you're starting to get a little bit of a feel for how we can control direction and speed using parametric equations. We have one more line example here at the bottom of the page. It says find parametric equations for the line y equals -3x plus 8. And that's really all it asked. It didn't give me any more information about direction or speed, so I can use kind of whatever I want for those. As I look at this line, I can see that the slope is clearly -3. And if I choose to write that as -3 over 1, that's going to define the b and the a that I need for the parametric equations. I also need a point. Now, there was no designated starting point on that line, so I can actually use any point I want from that line. An easy one would be 0, 8, the y-intercept, but I could use anything I want. I'm going to choose x naught, y naught to be 0, 8. But again, the problem didn't specify. So if you wanted to plug in, say, 2 here and get 2, 2, that would have been just as good a starting point. So using my information, I'm going to have x equals 1t plus 0 and y equals negative 3t plus 8. Or simply x equals t and y equals negative 3t plus 8. Since nothing was specified about limiting it to a certain portion of the line, I'm just going to leave it like that. Unless we state otherwise, the assumption is generally that t goes from negative infinity to infinity, which generates the entire line. All right, that brings us to the end of our discussion on lines, or parametric equations for lines. In the next video, we'll look at some other shapes and what their parametric equations look like.